Okay, we'll get started. Pick up your colored cards if you don't have them. So what we're going to do today is polish off logic, so to speak, and move to uncertainty. So just a couple of announcements. One is that a couple of you have asked me about summer jobs, and I said there's nothing, but it turns out there is a possibility of a summer job working on Alspace, it turns out. We'd like to do it from scratch again. We'll have Alspace 2.0. I'll probably write it in Python, keep it simpler, etc., move away from Java. There may be a job in that area. David Poole will supervise it. I'll be working with him, but he'll be the supervisor. And you have to apply right away. So I'll put a notice in Connect about this. But David Poole, who's poole@cs.ubc.ca. If you're interested, send him a message right away. It's just a possibility. We've found some extra money. It could be a USRA or it could be one of these science summer jobs. Okay. The other thing I wanted to mention was that we've been having trouble, some of you know, with the strips to CSP applet. It used to work. So there's some strange bug which involves using the XML download from the URL. Depending on which version of the applet you're using. You know, you can use a jar, an exe, a quick start, et cetera, et cetera. There are various ways to start the applet, depending on whether or not you have Java on your computer. So the combination of those things seems to be causing a bug in some cases. Now, let me just see, has anyone got it to work? Let's put it that way around. Question 1 of assignment 3. That's not promising. I managed to get it to work this morning. You sort of got it to work? I mean, the bug is that it ends up saying this arc is inconsistent. Yeah. Right, which it should never do. I mean, it should just make it consistent if you're making it. And it depends whether you're doing solving using arc consistency and you just make it arc consistent versus completely solve it, find all solutions. And that seems to vary too. So there are just so many different situations, and only some of them cause the bug. So I got it to work this morning, and I mentioned it in Connect. However, since then, people, including me, haven't been able to replicate that. So we'll keep working on it. If we can't fix it in time, you can just skip that. So it's question 1, parts D and E, I think. Well, you can still produce the CSP representation. That works fine. It's just solving it is the problem. So what involves solving the app, using the applet, you can skip that if we can't get it working in time. I hate to say this, but it maybe we'll give you an extension, but we're not giving you an extension now, okay? You've got 2 days to finish this assignment. Do everything else. If we get it working, we'll announce that, and then we would give an extension. But if we don't get it working, there'll be no extension, okay? So you have to get your assignment done by Wednesday. And then assignment 4 will be coming out on Friday as per the schedule on the homepage. Okay, so those are the 2 announcements I wanted to make. Are there any other questions? Say, in your midterms, figure out why you lost marks. 2 to the 16th, you should have multiplied it out. That's why you were supposed to have a non-programmable calculator. Right? Besides, all computer scientists know what 2 to the 16th is. But seriously, any issues where you lost marks, try and figure it out on your own, then talk to your friends. Most of you did really, really well in this assignment, in this midterm. So it's like highly skewed towards 65. Okay, I don't know if the statistics are available in Connect or not. Shafiq, do you know that? If the statistics are available?
Yes.
Yes, you can look at the statistics and see what the mean, the median, the histogram, etc. It's highly skewed. So, we knew it was easy. I knew it was easy. A lot of you walked out early without double-checking your paper. There's another lesson. Double-check your paper if you've got time. Stupid mistakes cost you. But we marked it really hard. We were really picky, and so because it was such an easy exam. And even so, you all did too well. So we'll make sure that doesn't happen in the final, okay? I apologize for an easy midterm. Okay, that was a joke. Any questions? Don't look at me like that. Shouldn't joke about these things, right? Okay, so we're going to talk about logic if there are no questions. No? Everyone's happy? It's not the same thing, but we'll assume you're happy. We're going to talk about finish off logic, which I was supposed to finish last time, but I went slowly. So you guys who know about Prolog, where did you do that? 312? Where did you run into Prolog? Quite a few of you have already seen Prolog. Functional language. It's 312, it used to be. Functional and logic programming. Prolog is not a functional programming language, it's a relational programming language. Okay, so most of you, I mean, maybe half of you know this material already on Datalog. Basically, this may be a new way of thinking about it. So I don't need to spend much time on it. It's covered in the book. We have an applet. It's part of assignment 3, so you'll learn it there if you don't learn it somewhere else. Very simple syntax with variables, constants. A term is either a variable or constant. And then you have predicate symbols. No function symbols, just predicate symbols. Things that are true or false. Predicates are applied to terms. And in this case, the terms are either variable or constants. If this were full Prolog, those terms could include function symbols applied to terms. So they're recursive. But here they're not recursive. They're just that's either T1 here is either a variable x or a constant a. And what we call atoms are symbols of this form, either just P, which is like a proposition with no arguments, that's like propositional calculus, or a proposition applied to terms. Okay, and then definite clauses are rules as before, and a knowledge base is a set of definite clauses. The semantics connects things in the computer to things in the world. That's in your head as a programmer, user of these systems. This is you, it's a funny shaped you here. And these symbols correspond to things in the world. That's the intended interpretation, right? So when you prove things in the computer using the Prolog interpreter, which is a theorem prover, so a top-down backchaining theorem prover, when it proves that things are true in all models, which means it must be true in the intended interpretation, because the intended interpretation, all the clauses are true. That's what you intend, and you're saying true things about the world that you mean to be talking about, okay? And the formal semantics are described in the book, but we're not covering them. You're not responsible for them. But you should be curious. Okay, so same old top-down proof procedure, but now we've got variables. And initially, so what you do, if we have this knowledge base here, is an atom in Allen R123, part of R123 CS building. So these are ground atoms. They have no variables in them. And here's a rule that has variables. X is in Y if Z is a part of Y and X is in Z. Right? So that's like saying something is inside something if it's directly inside it, or it's part of something which is inside something. You know, so it's recursive. And it's important that I put the recursive predicate here, the one in the head, not first, hopefully last. Hopefully it's tail recursion. And a good Prolog interpreter compiler will optimize that away, that recursion, into a tail call. But in general, if you put this first, then because of the way Prolog works, left to right, the selection function I talked about, it selects the first atom to try and prove that first. And if in were here, then of course this could recursively run away. I keep calling it self. It may not be in Prolog because it will indeed check the atoms before it checks the rules. But it's always good practice to do it this way around. Okay, so how do we deal with variables? So the idea is that you look for heads that match the query, and you substitute the variable in the clause with a matching constant. So if I have this query, which is ground, it's a ground query, but in general I can have variables in queries, but here I don't. Then I use this trick of constructing an artificial answer clause. Yes, if the query is true. So if yes is true, then the query is true. And in order to prove that, it will try and match this with the database. It'll try to match with that, but Allen matches with Allen, but constants never match themselves. This is called the unique names assumption in Prolog. That everything has a different name is a different thing in the world. There's a one-to-one between names in the theory and things in the world. It's part of the semantics. So R123 cannot match CS building, so that will fail. So then you'll have to use this rule, and that will succeed in matching the head, right? Matching in XY with Y here, bound to CS building. And so that'll be true if replacing this with the body, part of ZCS building, and in Alan Z, which actually X got matched to Alan here as well, that binding. Okay, so this is what's called unification. I mean, how many of you studied unification before? If you studied Prolog, you've actually studied unification. That's the binding mechanism for when you call a Prolog rule. You can have variables on both sides of the rule, and you pattern match the calling pattern against the head of the rule, and if you get a successful match, then you have substitutions for the variables. That's a simple version of unification. Again, we're not going to go into the details. It's covered in detail in the book right here, page 511. And in general, with function symbols, it gets more complicated. With Datalog, unification is a very simple, it's actually a very fast process. I mean, it's right at the heart of the Prolog interpreter, so it has to run fast. And unification can be done in linear time, which is important because it's like an atomic operation almost in Prolog and Datalog. Okay, so in order to prove that query, we reduce the answer clause to this clause by pattern matching this against this rule and getting this new body. Notice we've got from 1 atom to 2 atoms. So we want to reduce this to nothing, but it's gotten longer. That's okay. So now again we try and prove left to right part of ZCS building. We've still got some variables in here. That'll pattern match against this assertion. R123 is part of the CS building, room 123. Z is 123. And that will succeed because there's no body in this rule. And so now notice I've got to consistently substitute for Z. These are the same Z. So I have to substitute Z equal to R123 for Z here, and I've got this to prove. And of course that can be proved directly as a fact using that clause. Yes, so I've reduced the body of the answer clause to empty, which means it's now an answer. I've proved the theorem, and it'll return yes, top level. But then if you hit semicolon in Prolog, it'll say find another answer, because it's non-deterministic. It could find more than one answer. So it could try again. Is there any other way? It resumes the search where it left off here when it succeeded. So it might try this, might match that, and it will. So you get that. But then that reduction, part of ZR123, there's no part of in the head of a rule that will pattern match this, so that would fail. And it would then say there are no other ways to succeed, and it will return at the top level. Okay? So that's the Datalog interpreter. There's one built into Alspace. It's called the deduction applet, because it's deducing in propositional first-order logic with definite clauses. It's the deduction applet. You can try it on this. You can try the example I just ran. I encourage you to do that. And in assignment 3, question 4, you'll be using the applet as well. Okay, the only other issue we want to look at with Datalog is what happens if there's a query in the if there's a variable in the query, right? So I might say I'm interested in all things that Alan is in, and this will, because I have a variable in the query, this could be bound various ways, and Datalog can find multiple answers, right? So in that case, if there are any variables in the query, I have to take them into the yes clause. So the yes predicate now will take an argument, which is the variable. And as a side effect of proving this, if I do, that'll get bound and it'll return the value of x1. I don't just want to know the answer yes, I want to know what is Alan in. So here, what would happen when I run this? So it's clearly, this will work. So R123 will work. but it'll also return yes on CS building, just as it did before, because there are two things that Alan's in. He's directly inside R123, but R123 is inside the building, so Alan is in the building. So this in predicate can be thought of as the transitive closure of the part of relation here. Okay? And so you can use that, use this query in this, using this database, which I give you here, in the deduction applet to get a sense of how that works. And then the final thing I want to say about Datalog is what I already said, namely that in the SLD resolution proof, where SLD stands for selection linear definite, it always chooses the first clause or the matching head it finds in the knowledge base. So actually the ordering in the knowledge base is important in Prolog, which makes it a non-logical language. And here we're going outside logic, because in logic it doesn't matter what order you put the axioms in. No matter what order they're in, they're an unordered set. And even if you change their order, you should get exactly the same set of theorems proved. It's not the case with Prolog. For efficiency, right, it'll choose the first clause with the matching head. So that's why you typically put the ground bottom, the facts first. And for recursive function definitions, the clauses defining your base case have to appear first in the knowledge base. Otherwise, you get infinite recursions. That's the first thing. And secondly, as I said, I don't say it on this slide, but if you're doing a recursive call, you should put it at the end of the body if you can, so it's tail recursion. So compilers can optimize that out. But it also avoids getting into infinite loops. So, Datalog is a proper subset of Prolog, which stands for programming logic. It was developed by Alain Kommerauer in about 1972. And it was regarded at that time as very exciting because it's another step in computer science towards just stating the what about a problem. You just state the facts about a problem. You don't say how to solve it. You just state all the axioms that are true of solutions, and then you just have the interpreter find all the solutions, right? Now, there's some deviations from that ideal in Prolog. You have ordering effects that we've talked about here. We have things like cut. We have negation, which isn't properly handled, and so on. But to some extent, it comes up to that ideal. So, these are your learning goals for logic. You should be able to do all of this stuff. That's straightforward. And then finally, I just wanted to say a little bit more about logic. So we only covered just a teeny portion, of course. If you've done courses in logic, you know that. So this shows you what we have covered. The solid blue lines, we've covered it in exhaustive detail. Dotted line, we've covered some of it. So we've done PDCL. We've done quite a bit of semantics and proof theory, the soundness and completeness theorems we proved. PDCL is a subset of propositional logic, where you have disjunction and negation, which is a subset of first-order logic where you have variables. Datalog is a subset of first-order logic because it doesn't include function symbols. As part of propositional logics, we have satisfiability and satisfiability testing, which we covered in the CSP module. And the green here shows all the different applications of these ideas. There's a lot of applications of SAT in hardware and software verification, product configuration, and so on. It's very useful. And some of these other things we're not going to talk about in any detail. We will talk a little bit about the semantic web, cognitive architectures, production systems. So there are many logics beyond first order. Some of them are mentioned here. And we'll talk a little bit about ontologies. So, say here's full first-order logic. Second-order logic, where in second-order logic, you not only can have individuals that can vary, I can actually vary over a predicate. So you could say for all predicates, such that the following is true, then this is true. Right? Non-monotonic logics, and a monotonic logic, which are all the ones we've seen so far, every time you add a new axiom to a theory, you get more theorems. Okay, you could never reduce the number of theorems when you add an axiom. However, in non-monotonic logics, that's not true. They behave rather strangely, that you can add additional facts and things will become false. Right? So, for example, the classic example is Tweety. If I tell you Tweety's a bird, you would conclude that Tweety can fly, and normally it's the case that birds can fly. But if I tell you Tweety is a penguin, that's an additional fact about Tweety, then we conclude suddenly he can't fly. So it's gone from being able to fly to not being able to fly. And that's useful to model common sense reasoning. Modal logics, logics of time, and so on are quite useful. We cover a little bit of this in some of the more advanced chapters in the book. But to focus on actually useful things, think about a software agent, which is actually a travel agent or someone booking a weekend in Victoria or whatever on your behalf, knowing all your preferences and knowing everything that's available out there on the web, doing a good job of it. The Semantic Web is a whole effort by the W3 consortium to try and make HTML pages machine readable, basically, because HTML is not, doesn't have any semantics. Okay, so we'd like to know what web pages mean. And at the moment, this almost all has to be done by a human or using very simple Google-like association techniques. So this travel agent might want to ask, you ask it questions like this. What's a typical flight to Mexico for a given date? What's the cheapest vacation package to someplace in the Caribbean? Blood, I want to make sure the hotel has a white sandy beach and scuba diving available. TripAdvisor, et cetera, it doesn't do well on queries like this that are based in English, for sure. So you can use natural language processing, and Watson and Siri are good examples of this, but they're a long way from the ideal because they don't understand pictures, they don't understand implicit information, et cetera, et cetera. So the Semantic Web. So these are languages and formalisms based on logics, okay, including information in more structured format, and they also have semantics. Okay, so I'm not going to go into any detail. We do cover again in the book, in chapter 13, quite a lot of ontologies. You're not responsible for it in any detail. But if you're interested in this topic, there's a really good tutorial at this website on Semantic Web tutorial. It says 2011, but Guy Herman keeps it up to date. So it's got the latest on semantic webs. But I'll just mention a few classic ontologies. I mean, people are putting a huge amount of work into this effort, and it's turning out to be quite useful. There's a e-business ontology for products and services. So if you were searching for people who could fill a certain kind of contract, where you have certain formal specifications for the contract and you want to search the web for people who could satisfy it, you have to be able to reason about different kinds of contractors, what their specialties are, what their deadlines are, and so on and so forth. The National Cancer Institute has an ontology of cancer types, 58K classes, this open biomedical ontology, gene ontologies, open psych. It's a really interesting project. It's been going for about 30 years now. Initially, it was based on a very informal notion, but now it's based much more on formal logics. And the idea is to build an ontology of common sense. Like what is a cup? What is a glass? What do they have in common? Well, they both contain liquids, etc. So if you ask for, I'd like a coffee, would you rather have it in a cup or a glass? The system would know that both could contain liquids, but glasses aren't so great because they conduct heat, and cups would be more insulated, so on and so forth. Again, open psych. It's an open access project that's used quite heavily now for lots of different things. So that's just a quick survey of some of the uses of logic to show it's not useless, it's very useful. So we come to a natural divide in the course where we're going from deterministic type of environments. We've done constraint satisfaction, logic, and planning in a deterministic model, and now we're going to uncertainty, which is a very major part of modern AI. So we're going to talk about probability theory in itself, and then Bayes networks. And again, these are the reasoning techniques that we're going to use. These are the representations, Bayes networks, decision networks, Markov processes, and these are the reasoning techniques we're going to use. Same notation as we're using over there. So this is really today's lecture. Okay, so these are the textbook sections, which you should read. You've got your colored cards. We're going to start with an introduction to probability. And this may not, I mean, how many of you think course is in probability? A course in probability? At least one. Okay, so not a lot. It's interesting. Of course, you all should have. It's so important, not just for AI, but machine learning, but for many other areas of computer science these days. But the view we're going to give you a probability here, it may be different from the one you got in your probability course. So there are two kinds of probabilities. There's subjective probability, and there's so-called objective or frequentist probability. Subjective probability is what we're going to talk about, and that's concerned with an agent's beliefs about the world. And many people could have different probabilities for a given event, because your probability for an event, which we think of as, or the probability for a statement, is your degree of belief that it's true. Okay, it's either true or false, but you don't know. And so your uncertainty would be represented as your probability that you believe that it's true. As opposed to the objective or frequentist version of probability, where you think of probability as, in the limit, the sum of doing infinitely repeated experiments, the probability is the frequency that a certain event will occur, given some random sampling from some space of events. And that's the same for anyone. It doesn't matter who does the experiments, right? And we just think that's profoundly wrong. Okay? And certainly for what we're doing, when we're talking about agents having beliefs, it's clear, and I'll give you some examples why we think it's wrong. Okay? So, where does uncertainty come from in our world? Well, we already talked about this, right? There are two kinds of uncertainty for an agent. You don't know what's true in the world because you're not sure what you're seeing. Your senses are uncertain. Okay, you may not be able to fully observe the world, or the sensors themselves may be faulty or unreliable or noisy. So for example, you know, how many people are in this room? That we can all see, all the people in this room, but I don't know how many there are. Say about 70? About 100 represented per course, so 30 people who are watching the video probably afterwards, maybe. So we don't know exactly how many there are. So we need some kind of probability distribution to represent my uncertainty about the belief of the number of people in the room. Someone in the back may have counted the people in the room. They know exactly that there are 71. Okay? So there are two different probabilities there. What disease does the patient have? You don't know. You've got lots of symptoms, but the whole point of going to the doctor is to find out what you got. Or if you're playing soccer, because of your limited field of view, you may not know who's behind you. Okay? So that's about your knowledge of the world. You're not doing anything. Just, you cannot fully know the world. That's just impossible for any agent, except God. So the other kind of uncertainty is you don't know what's going to happen when you do something. Okay, we assumed in planning you did know what was going to happen when you do something. We had this, omniscient fortune teller assumption that whenever you do something, you know exactly what will happen. Right? But that's clearly an idealization, to put it mildly. In some worlds, you might be able to get away with that, but in the real world, it's very unusual. So if I work hard, will I get an A in this course? Well, maybe. Maybe not. Will this drug work for this patient? Maybe, maybe not. When I kick the ball, will it go in the goal, or will the goalie save it, or will it go off to the side? Who knows? Well, I could probably estimate the probabilities of each of those happening. I don't know for sure any of them, right? So you've got to handle uncertainty. And these deterministic domains are a real abstraction. And because it's an abstraction, we're simplifying the world, you get more powerful inference techniques. Like CSPs are very certain, right, how they're dealing with things. So a lot of those inference techniques don't fully generalize. Some of them do generalize in interesting ways, but they don't all generalize in ways that you'd like. But for that simplification, you get an advantage of efficient reasoning. But once you don't make the abstraction, you've got a more expressive and general representation, and the usual trade-off is the more powerful your representation, the more complex the procedures, the decision procedures or inference procedures, working with them. It's always this tension in AI between the power of the representation and the power of the inference procedure. Okay, there's no free lunch. However, there was a big breakthrough in the 80s in so-called Bayes nets. Jutta Perl and some other researchers discovered efficient ways of reasoning with probability. Before that, it was always thought to be just too hard, so let's just deal with certain worlds and logic. Okay, but that breakthrough doesn't solve all the problems, but it does make it tractable in many important cases. And it takes advantage of a fact about the world, that the world is typically local. Causal effects are local. When I do something in this room, it mostly affects things in this room, not in other rooms, not in Australia, et cetera, et cetera. So I can factor causality into my representation, and the effects of most actions, like picking up this cup, it affects nothing else except, because my arm has to move, but the water moves with the cup. I have to know that the water moves with the cup, but I also have to know that my laptop won't move, even though, you know, physicists with a theory of gravitation would say, of course it moves. When you move this there, the gravitational field of this changes and moves the laptop. Well, maybe, but for our purposes, it doesn't move. So that's important. And this so-called new AI, which is also about, you know, embedded and emergent systems. So this is one of the buzzwords that taken all. Interesting. Someone stole all those. Embedded, embodied, emergent, the 3 M's. So that's sort of part of what we call the new AI, but also uncertainty is part of the new AI. And learning, very much part of it. It was part of the old AI too, but it didn't get very far. Again, there were breakthroughs in learning in the 80s. And part of it was due to this breakthrough in Bayes networks. But this shift from logic to probability is a shift in emphasis, but it's not a dichotomy. It's not like either you choose a logical representation or you use a probabilistic representation. Because there are many things you can do in logic you just can't do in current versions of probability theory, like reasoning about individuals and reasoning about whole classes and ontologies with uncertainty. That's like a current research area, right? But our probability theories are actually written in logic. If you look in the book and you look at, we give you a set of axioms for probability theory. We're not going to cover them in class because they're a little boring. But there is a complete axiomatized version of probability theory in logic. Okay, so it's not like you choose one or the other. It's not a dichotomy. So as I say, that's the new frontier, is combining logic and probability. But I would recommend this article. It's Peter Norvig, who's, we had him come last year and give a talk. You may have seen it. One of the heads of research at Google. He also has an AI text with Sebastian Thrum. So this article talks about the machine age, and the bottom line, I mean, he's not the first, lots of people said this. The things we thought were hard turned out to be quite easy, in fact, to do. You know, many world-class chess players, done. Theorems and proving theorems in mathematical theories like integral calculus, done. But, you know, just being able to determine that's a cup, this is a laptop, that's a watch, something we still have trouble with. I mean, we can just about do that now with our robots, but it took 50 years to get that far. So we're like at the level of like a 3-year-old child in terms of visual, not quite, maybe a 2-year-old, not quite. We're not even up to good dog standard. So vision, and a lot of these things are perceptual. Okay, things that don't involve perception so much, like chess and theorem proving, we could do. We could do crisp reasoning, fast reasoning, etc. But things involving perception and action, like robot soccer, which was, you know, the task I introduced to AI, they were really hard, and they still are really hard because they involve uncertainty, and we don't quite know yet how to integrate uncertainty into our knowledge representations. So that's a message from Peter Norvig. So this is to motivate you to think about probability. So as I said, our version of probability may not be the one you've encountered before. So we're going to think of probability as a measure of ignorance, right, or uncertainty. That's a formal measure, and it's relative to an agent. Whenever I say a probability, you should be able to say which agent are you talking about that has that probability. It's always possessed by an agent, okay? Because it's a measure of the agent's degree of belief in propositions about the state of the world. And one faulty notion of probability is sort of measuring how true a proposition is. Like, George is tall, 0.6, which means that he's taller than average, but he's not super tall. That's not what we mean, okay? And that's what's called fuzzy logic, and you'll encounter fuzzy propositions and so on. That's not what we're talking about. Every proposition in our world is either true or false. We just don't actually know which is which, right? So when you roll a fair dice, if I tell you it's fair, then what is the probability the results is 6? Well, there's no answer to that question. You might have said 1/6, but you're wrong, because there's no such thing as the probability. It's actually, if I know that it's fair, then my probability is 1/6, which is 16.7%. It's either a 6 or not. I don't know. I haven't looked at it yet, right? When I look at the dice, then my probability will be either 1 or 0. When I look, it's either a 6 or it's a 4 or it's something else. So I know exactly then. But your probability, if only I look at the dice, your probability hasn't changed. You don't know yet what it is. So your probability is still 1/6. My probability is either 1 or 0. They're completely different. Okay? I could tell some of the class, well, I've looked at it, and I know that the result's even. Right? So I'm giving you additional information, but not enough to identify the state. Now what's your probability? Yeah, it's about 1/3. Right? So some of you have 1/6, some of you have 1/3, and I have 0 at 1. So everyone has a different version of probability for an event. Okay? That's a critical lesson, and that's why we call it subjective, because it's relative to a subject, the subject who knows things. We're talking about knowledge and belief and ignorance and so on. So different agents have different degrees of belief. This is a subjective interpretation of probability, as opposed to the frequentist objective notion. And the book goes into more boring detail about that distinction. Okay. So we're going to measure probabilities in terms of a number between 0 and 1, but that's purely artifact. I could have used 0 to 100 or -1 to 1. It didn't matter. We'll use 0 to 1, because most people do. That's a convention. So the probability, the roll of a fair dice came out as a 6, is 1/6, in the absence of any other information. If I'd had other information, I'd have to put it in here. Like, given that it's even. I'd have to say that included in the statement, right? Then it would be 1/3, right? So if you got your cards, we're going to do a few flashcards, wake you up. So the probability of f equals 0, what does that mean? Probably true, probably false, definitely true. So yeah, it's definitely false. I mean, 0 and 1 are exceptions. They're the only case when you know exactly what the truth status of the proposition is. It's either definitely true or it's definitely false. Okay? So we're going to give some meaning to what we do with this notion of probability theory by talking again about possible worlds. So we're all going to tie this back to our same theory we had before. This is not new. Okay, so as I said, probability theory is a system of logical axioms and formal operations for sound reasoning under uncertainty. We're not going to go into the formal logical version of probability theory, but it's all in the book. But the basic element is this idea of a random variable. And this is the same sort of variable we've already seen in CSPs, planning, and logic. Okay? It has a value. The distinction now is that the agent doesn't know what the value is necessarily. They're uncertain about it. So as usual, we'll have the domain of x. This is a value that x can take. And we'll have various sorts, technical meaning of sort, like things like Boolean, categorical, and numerical. So Boolean is true or false. Categorical is one of a certain finite number in a set. Numeric is where you have a scale, and it could be either integer or real, so on and so forth. We're primarily going to talk about Boolean and categorical variables, but everything we say will apply to numeric variables as well. So again, we want to look at the semantics. Okay, so, and again, we do this through possible worlds. Okay? So suppose we're only interested in 2 Boolean variables for an individual. They either have smoked or they haven't smoked, or they are smoking and they aren't smoking, and they have cancer or they don't have cancer, right? So then again, here's world 1. In a world, each of our random variables has a value, okay? So in world 1, smoking has the value t and cancer has the value t. World 2, smoking has the value t and cancer has the value false, and so on. So here's world 1, world 2, world 3, and world 4. So there are 4 distinct possible worlds. We've seen this over and over again, how to enumerate the number of worlds. And then we have some notation here. We use the same entailment notion. So in a world, x equals x means that variable x is assigned the value x in this world. Okay? So in world W, x equals x is forced. It's entailed. Okay? And what we're going to do now is that we haven't done this before. Up till now, we just said, well, all the worlds have roughly, they have equal status, right? They're all equally likely, say, or whatever. I don't even know how likely they are. They're just all different. But now we're going to talk about how likely they are, and we're going to use what we call a measure on the possible worlds, mu, which will eventually, sometimes, importantly, sometimes correspond to probability, such that the measures on all the possible worlds sum to 1. So this is like the many worlds theory in physics, right? There are really a very large number of universes out there. We just happen to be in this one. And each one has some measure attached to it. So same thing. There could be 4 possible worlds out there in which the patient is smoking and has cancer, is smoking and does not have cancer, and so on. They're all different worlds. If I have a proposition f, which could be a compound proposition, it could be x is equal to 6, or it could be x is less than 3, or it could be x is equal to 3 and y is greater than 7. So I could have any kind of proposition here, f. The probability of a proposition is just summing the mass of the worlds. Okay, you think of these having mass. So I'm summing the measures of the worlds in which that proposition is entailed, is true. Okay, so that's why measures and probability aren't exactly one-to-one, because in order to get the probability of a statement, a compound statement, which is, it could be like x is equal to 2 or x is equal to 7, right? That statement is true in the world in which x is equal to 2, and it's true in the statement in which the world is x is equal to 7. So I'd have to add up the mass of those 2 worlds in order to get the probability of the statement x equals 2 or x equals 7. Overall, right? So that's what this summation is doing. It's just summing over the worlds in which f is entailed, forced to be true. And that's a critical definition right there. So this is what we call possible world semantics, okay? So let's give a more concrete version of that. So we could be interested in the weather in Vancouver. Initially, we'll start out with just one Boolean variable. It's in Vancouver, it's always either sunny or it's cloudy, right? My numbers, the probability of sun is much less than 0.4. But anyway, suppose it is. So there are 2 possible worlds. World 1 in which the weather is sunny, world 2 in which it's cloudy. And so I'll put the measure for this sunny world here. I just write probability of whether sunny is 0.4. What's the probability of weather equals cloudy? There are 4 possibilities. We don't have enough information. It could be 0.4, it could be 1, it could be 0.6. Of course, it's 0.6 because it's either sunny or cloudy, and just use intuition for this. So remember this definition here and what it means for a proposition to be entailed in a world. And the probability measure has to sum to 1 over all possible worlds. That's how we got 0.6. And the probability of a proposition is defined by the sum over all worlds in which it's entailed to be true of the measure of those worlds. Okay? So it's a very concrete notion of measure attached to the world. And that's the basic idea of probability theory, is attaching measure to world. And that's something the agent has to do. It's his initial belief in, given all these possible worlds, what is the various ways in which things could be true. And the agent could learn that. You could just look at all the weather statistics for Vancouver and count the number of days. You could use frequentist things if you wanted. But if I told you, and you come to Vancouver on a sunny day, it's always sunny in Vancouver, that agent would think the probability of sunshine is 1 and the probability of cloudy is 0. That's a different set of beliefs. So you can come across these measures any way you want, but again, they're relative to the agent. Okay? So if we add another variable like temperature, it could be hot, medium, or cold, then we've got 6 possible worlds. And if I write down the measures that I believe these things are likely to co-occur in, then I get those numbers. And so what's the probability of being cloudy and cold? Well, first of all, it says add those up, and that's 8. So it's clearly got to be 0.2, right? Yeah. This has to be 0.2 because we know the measures over all possible worlds have to sum to 1. So that's the basics. And so we've introduced this idea of measure. We've introduced the idea of joint probability distributions, basically, where we have more than one variable covariating, and how you have to assign measure to each set of possible values for those multiple variables. Okay? So the simple case, suppose the possible worlds are simply assignments to one random variable. Then we talked about a probability distribution on a random variable is a function from the domain of the random variable into 0, 1, closed interval 0, 1, such that x maps to the probability x is equal to little x. So you've encountered this if you've done any probability theory. This is the probability density function. Okay? If it's infinite, or if it's a real, or it's even if it's an integer, you'd call that a probability density function. We're going to focus on the finite case just because we're going to use summations. So we've talked about joint distributions now. So you can jointly vary numbers together, right? So here we've jointly varied over 2 variables, weather and temperature. So in general, the random variable x1 through xm will vary over the cross product, the Cartesian product of each of the domains, which is taking all possible pairings of values. So there's the joint probability distribution for the random variables weather and temperature, and each row corresponds to an assignment of values to the variables and the probability of this joint assignment. That's the simple case where we're only interested in the joint assignment. Okay? So that's the joint probability distribution. And in general, of course, you have more than 2 variables. You could have n variables. And you could write the probability of x1 is equal to x1, xn is equal to some value xn. You could also just write it this way. The probability, this is just a single statement. This is a logical form. Instead of using n different arguments to the probability function, we might write it this way, where this is the probability that some logical statement is true, which is true if and only if they each have their values, right? Once we've done that, we want to talk about what you call marginalization. You may have too much information, and you want to project out some of the variables. So, for example, if I give you all this data about Vancouver, these are my beliefs about whether it's sunny or hot. Suppose we're only interested in what's my probability that it's going to be hot today. I don't know whether it's sunny or cloudy. So I need to project that out. I need to marginalize it out. And the way we do that is just, in this case, probability of x, you sum over all the variables you're not interested in the joint probability distribution and get a marginal distribution here. In this case, it corresponds to summing out a dimension in the table. And the new table, of course, still has to sum to 1 because it's still a probability distribution. So if I want to know the temperature's hot, I look for all cases where it's hot, or 2, sunny or cloudy. They're mutually exclusive, so I can just add these 2 numbers together and get 0.15 there, right? Similarly, I can marginalize out the weather when it's mild. The 2 cases are sunny and cloudy. 0.2 and 0.35 gives me 0.55, and so on. Okay, we'll stop there and pick it up again on Wednesday.